Okay. So, well, thank you for the invitation to come to Florence, which is surely one of the gems of our planet, and the invitation to speak at the tude of one of my scientific heroes, all of our scientific hero, Galileo. Um, yeah, I was asked to speak about um, Log-CFT. So I won't speak about Log-CFT. More precisely, what I'm going to do in my first part of my series of talks, I don't know how long it's going to take. I'll do an introduction to, um, to CFT and VOAs. So CFT means conformal field theory, and VOAs mean vertex operator algebras. Okay, and then in the second part of my talk, so Log-CFT so my focus will be on, I know that most of you are physicists, and so the CFT language is probably more familiar to you than the VOA language, but I'm not a physicist, and the VOA language is more familiar to me than the CFT language. And so I'll use this first part as a motivation for and a general description of a VOA. So a VOA is a magical box, but like most magical black boxes, you don't want to look inside. And so in my talk, I'll describe for you. I'll motivate what it's about. I'll try to sketch the axioms of it. But Borchards, the first person to write down essentially the axioms of a VOA, said you either know what a VOA is, or you don't want to know, and that's not an exclusive or. And so I don't want to dive too much into the blood and guts of a VOA because it'll destroy the illusion that this is actually a beautiful area. And but it is a beautiful area. So the impact of VOAs, or more generally CFT, string theory, on mathematics, of course, is really profound. Galileo, a few centuries ago, initiated a revolution, but not just a revolution in physics, it was a revolution in math as well. Classical mechanics gave us calculus, for example. It eventually gave us symplectic geometry. So revolutions in physics are great for mathematics. And so 100 years ago or so, Fermi was part of another revolution, a far more profound revolution. And the impact to mathematics of that revolution is still just trickling through. We still haven't absorbed quantum field theory into mathematics. And so one of the ways that we are is through conformal field theory and VOAs, as I'll try to explain, is a mathematical way to try to understand what a CFT is. And so, but anyways, I don't want to dive in too much into the details. So I'll give you some taste of what a VOA is, CFT is, and then we'll start to look at its properties. Now, a log-CFT is a CFT where things are starting to go wrong. And so the second part of my lectures will talk about non-log CFTs, or VOAs, actually. Non-log has another name. It's called rational. So I'll describe VOAs where everything works out beautifully. And then the third part of my series of talks, third and final part, will be to address the thing I was asked to address, which is, I don't know if I'm getting excited or not, but the chalk is slowly breaking apart. Log CFTs, or more precisely VOAs, log VOAs. Okay, so that's the basic sketch of my series of talks. Okay, so maybe what I should do first is give you the big picture of CFT and VOAs. So the idea comes from perturbative string theory. So in perturbative quantum field, in quantum field theory, you're interested in computing amplitudes, scattering amplitudes. and, and you never can. And so what you do is the main way that we try to do this is through perturbative expansion, some kind of a Taylor expansion. Um, and the terms in this Taylor expansion can be captured by Feynman graphs, which then translated into some kind of a path integral, which we then can imagine calculating. And so in perturbative string theory, things are far more wonderful. And so your histories, as you all know, I'm sure, better than me, I'm sure, your histories are, here are your two strings. Here are your two strings. And they come together, let's say. They split apart. They come together again, and actually, they just come together. And so we've traced out a surface, of course. So the Feynman graphs are surfaces. In this case, the surface looks something like this. And, can have arbitrary incomings, outgoings, genus can be arbitrary, et cetera, et cetera. So to each one of the Feynman graphs, we get a Feynman integral, and we get a term in the perturbative expansion of that particular amplitude. Now, the way to proceed is to break up your surface into vertices. Vertices look like this. A pair of pants or a sphere with 3 punctures. And so, so here's one way to do this. And so when we're writing down the integrand of our Feynman diagram, of our Feynman integral, each vertex is going to contribute a part to that integrand. Each vertex contributes an operator. And so that operator is called a vertex operator for obvious reasons. So this is the contribution of a vertex, a y, to your integrand. And where you sew these things together, you're just composing the relevant components of your operator. Okay, so what a vertex operator algebra is an algebra of vertex operators. Now, so we have this complicated Feynman integral that's going to tell us a particular term in our perturbative expansion of the amplitude we're really interested in. So we can interpret this as a correlation function. So each term in the perturbative expansion is a correlation function of a vastly simpler quantum field theory, namely a CFT, a conformal field theory, whose space-time is the surface that we're on, the world sheet that we're on. And a quantum field theory, this is a point quantum field theory, it's not a string quantum field theory. The quantum fields for this quantum field theory are our vertex operators. So the vertex operators are the quantum fields in an ordinary quantum field theory with an enormous symmetry on a two-dimensional space. And so in principle, at least, these correlation functions can be computed. You don't need a perturbative expansion to work out what these correlation functions are. So it's a reinterpretation of the terms in the perturbative expansion of string theory. So that's what conformal field theory is, and that's where VOAs are coming in. Okay. I'm not saying perturbative string theory equals conformal field theory, but it's pretty damn close. So really, in perturbative string theory, you want to add up all of these amplitudes. You want to add up contributions from infinitely many different conformal field theories, or more precisely, there's one conformal field theory that exists on all these different surfaces. Genus is ever increasing, and so you add up all these contributions. That doesn't make any sense from the conformal field theory point of view, but it's what you want to do in your string theory. So it's not exactly the same thing, but it's pretty damn close. So basically, perturbative string theory, at least to me, equals CFT. So if you believe in string theory, then, well, there's going to be some non-perturbative effects that certainly you're also interested in. But if you believe in string theory, I think you believe in conformal field theory. So I'm a mathematician, so I don't care whether string theory describes the physical world or not. What I'm interested in is that string theory has begotten all kinds of incredibly profound mathematics, and this is just the beginning. So, so that is that. Okay. So conformal. So, what is a CFT? More precisely, CFT. When I say CFT, what I mean is a conformally invariant. I'll remind you what conformal means. It's a quantum field theory on a two-dimensional space-time. Now, there are many different mathematical approaches to try to make sense of quantum field theory because everyone's, or most people, surely only the idiots would dispute this fact. Quantum field theory is going to be has been and will continue to be very significant for mathematics. And so we want to understand mathematically what a conformal field theory is really all about, what a quantum field theory is really all about. And so there's many different mathematical approaches over the last few decades to try to make mathematically precise what a quantum field theory is. It's not a trivial thing to do at all. It took I don't know, 100 years or 150 years to make mathematical sense of calculus. So this is way more profound. So it's going to take us a long time. So the 21st century is where we'll really absorb quantum field theory into our mathematics. Anyways, so there are many different approaches for this, and one of the oldest, maybe it is the oldest, it's not the most inspired, surely, but one of the oldest, one of the most established is the Whiteman axioms. So the Whiteman axioms are a mathematical approach and mathematical axiomatization of quantum field theories. And so the idea is that it starts, the fundamental building blocks of the Whiteman axioms are quantum fields. So it takes quantum fields really seriously, and it tries to make sense of what they are and the properties that they have. If you apply the Whiteman axioms to conformal field theory, then what you get are the VOA axioms pretty directly. So there's other approaches to QFT, and therefore there's other approaches to CFT, and therefore there's other axiomatizations, mathematical axiomatizations of CFT, and they'll give you things that also have incredible properties. They tend to be newer and they're not as well explored, and so that's why I'm focusing on VOAs, the Whiteman axiom approach. But maybe 50 years from now, the VOAs will be in sort of the backwater, and we'll be much more passionate about conformal nets or something like that, which actually seems to me to be a more profound approach to quantum field theory. But anyways, the standard approach, the one that we understand the best, is VOAs, since that's what I'm going to focus on. So it follows pretty directly from CFT. So I'm going to explain this in a little more detail over the next few minutes. Okay, so the first big question is, why is two dimensions so important? Well, first of all, conformal transformations are transformations which preserve angles and not necessarily lengths. And so in Rn, the group of conformal transformations does anyone know? Yeah. It's isomorphic to this. And this is true for all n. There's nothing special about n equals 2. What is special about n equals 2 are the local conformal transformations. These do not form a group, they form a Lie algebra. Local symmetries always form a Lie algebra. The global ones form a group. And so the local ones, there's lots of local conformal transformations. So local conformal transformations of Rn, when n doesn't equal 2, are the Lie algebra. Little s, little o, n plus 1, 1. So this is over, these are reals, over the reals. But when n equals 2, the local conformal transformations are much more exciting. And we know this from complex analysis. So all of us, I'm sure, have taken a complex analysis course at some point in their lives. And so if we look at, so here's a copy of R2. I'm going to think of it as the complex numbers, though. And so if I take any function when the derivative doesn't equal 0 is locally, so as long as this is a holomorphic function in a neighborhood of z0, and the derivative at z0 is not equal to 0, this is locally conformal. So for example, let's look at f of z equals z squared. Well, if we were to take, say, the 45-degree line and we square it, then this changes to a 90-degree line, and it's definitely not conformal, but that's because the derivative of this at 0 equals 0. If we look at this 45-degree line at any other point, and then we square this segment here, this part of the real axis, and this part of that 45-degree angle line, you can work it out for yourself. I'm not completely sure that this is the correct answer, but this is what I got. I got something that looks like a parabola. So lines don't go to lines, but the tangent at this point was 45 degrees, and it stays 45 degrees. So you get something like that. So anytime you have an analytic function whose derivative at your point isn't 0, then you get something that's going to preserve angles. So it'll just be a local thing. It's not going to be a global thing. You can't compose these things like you can for a group. But you get a Lie algebra worth of these things. And so it'll be infinite dimensional. So you get an infinite dimensional Lie algebra of local conformal transformations when n equals 2, and it'll only be finite for any other n. So n equals 2 is very special. For a conformal field theory, for a quantum field theory, the local symmetries are the crucial ones. So we'll talk more about this a little bit later, but for now, let's push this idea a little bit further. And so our Lie algebra is, well, you can find a basis for it. I'll give the basis in a few seconds. You can find a basis for it that obeys this. It's a Lie algebra, so we should look at the brackets of these things. I'm assuming that you all know about Lie groups and Lie algebras, but we're not going to dive too much into these. So if you don't, it's not a big deal. And this is going to be, one way to write down this bracket is it's going to be this. And so there's a basis for your infinite dimensional Lie algebra, and the basis vectors satisfy this very simple commutation relation. And so one way to see this is to look at, so what's going to generate these local transformations are these things, these operators. And so let's do the commutator for 2 of these operators and see what we get. Well, this is, we have to remember to do the Leibniz rule here. So we get Zm, we get the derivative applied to Zn dz minus the other order. I'm not very good with calculations, so this is the sophistication of my examples. And so if we do this calculation, we'll get an n coming out here, and we get a z m plus n minus 1. And that gives us a d dz. Plus, by Leibniz's rule, we get also the derivative of this thing. So we get the derivative of this times this, plus the derivative of this times this. So we get, you can see why I'm not good with calculations, because I get cramped into some corner and I absolutely refuse to turn the page. And so, but that's fine. I'm sure you all sympathize. And so we get the other thing, which is Zm plus n, second derivative of dz. So that's this term. And then we're going to subtract the other term, which is going to be an m, z, m plus n minus 1, dz. And we get another minus sign, the derivative over here. So we get a z n plus m d squared dz squared. I'm sure you can't read that. I can't either. But I know the answer. So apparently lawyers say that you're never supposed to ask a question in the courtroom that you don't know the answer to. And so I never start a calculation that I don't know the answer to. So I'm willing to start this calculation. And so what we get is half the terms cancel. So this term survives the first term. We get an n z m plus n minus 1 d dz. And the d squared terms cancel. And the other term is m z m plus n minus 1 d dz. This isn't quite what we wanted. So so what's going on here? Did I screw up? I thought I knew how to do this calculation. Can anyone help me out? I ask a question when I'm stuck, and so I'm hoping that inspiration will strike. If it doesn't strike me, it'll strike you. Well, there's no law that says that ln has to equal zn, blah, blah, blah. In fact, the thing that works is take ln to be minus. That takes care of our minus sign. We also have a problem with m plus n minus 1. And so we do a z, I think we do an n plus 1 d dz. So let's see if this works. So if we do this, then what we get is, well, we really would have a plus 1 here and a plus 1 here. So that means we'd have a plus 1 here. So when we do all this, we'd get a plus 1 minus 1. So I think that works out to plus 1. We get an n plus 1. Who cares about the d squared terms? And here we get a plus 1. And I forgot to write down my m. Oh, no, that's a squared term. We can ignore that. Here we get a plus 1 and an m plus 1. Okay, so what it all works out to be is, so this thing here, if we do this with this thing, with the m's and the n's shifted and a minus sign thrown in anyways, what you get is, you get L m plus n. You get exactly what you're supposed to get. Okay. So it's just arithmetic and it'll work out. So there's no law that says that we have to. So these commutation relations were chosen to look particularly nice, and so to get them, we have to be a little bit odd with our definition of the L's. That's okay. Okay, so so I think that's all I want to say about why two dimensions are special. So we're going to require our quantum field theory to respect this infinite dimensional Lie algebra of local symmetries. So we'll see later how we do that. Okay, what comes next? Okay. I think this story is really a pretty story. If I don't seem enthused, it's because I got into 2 hours of sleep last night. So the most important, so there, a CFT, a VOA, should make sense on all surfaces. The most important of all these surfaces, the most boring of all these surfaces, is the cylinder. So we can think of our cylinder as, let's make it a semi-infinite cylinder. And so it's going to correspond to a string that exists at time equals minus infinity, so at the beginning of the universe, and it propagates to the present time. So it's going to be described by a semi-infinite cylinder. The cylinder looks like this, and it goes back in time to t equals minus infinity. This is t equals 0, let's say. So our time is going to be, so our parameters on our cylinder here, our world sheet, are going to be t and they're going to be some angle parameter, which is where we are on our circle. I'm sure this is all very familiar to almost all of you probably. Okay, now the magic of conformal symmetries is, conformal transformations, is we can map this. To a much simpler picture. We can map it to the punctured disk. So this is the punctured disk. It's the magnitude of z is less than 1, and so the map is going to be e to the. All there's different maps I could take, but here's one, I theta, and I could also take its complex conjugate. That would also work fine. So t equals minus infinity, as you can confirm for yourself, goes to the dot in the middle, and the present time corresponds to the circumference, the outside of this, the boundary of this disk. Okay. Now, more generally, any of these things that we're considering, so any of our world sheets, so we can have world sheets that look like all of these world sheets can similarly, it turns out, be transformed into, in this case, it'll be a genus 2, a double torus with 1, 2, 3, with 5 points eliminated. All of these are semi-infinite. So when you're doing your quantum field theories, you always take this fake limit off to infinity. So these are all semi-infinite cylinders. And so those are all conformally equivalent to something that lives here. And so there's lots of different double tori with 5 punctures removed. In fact, there's a moduli space of these things. And the dimension of this moduli space grows linearly with the genus and with the number of marked points. This one is a big one. And we'll talk more about this later. But you can generalize this thing here to any of these surfaces. You only have to consider compact surfaces with punctures, with points removed. Finally, many points removed. Okay, why am I saying all this? Well, this will come in handy later. So one thing that we're going to need is the Hamiltonian of our quantum field theory. So the Hamiltonian, the energy operator, is proportional to the time derivative. Well, we've carefully eliminated our and I've erased it as well, oh no, it's over here. So this is, we've eliminated our t variable. We're now in the land of z's. So what does the Hamiltonian look like in our z variables? Well, this is just the chain rule. So this is the partial derivative with respect to z of the partial of z and the partial of z bar. We think of t and x as being independent. We could think of z and z bar as independent. Who cares that this doesn't make maybe total sense? It's not my problem. And so we get something that looks like this. And so the derivative of z with respect to t is itself. So we get z d dz, and the derivative of z bar, which is just a plus sign here. Which one I call plus and which one I call z and which one I call z bar doesn't matter. And so this one's going to be z bar d. And in terms of our definition of L's that are given up there, this is going to correspond to minus L naught minus L naught bar. So we're treating z and z bar as independent of each other, so we get 2 copies of the conformal symmetries. One corresponds to complex conjugates, so it changes angles up to a sign, but otherwise all is good. And so we get a different copy of these conformal algebras. And so our Hamiltonian is the L naught part of our conformal symmetry. So the fact that we get minus signs here is merely, is just, Hamiltonian is You can rescale it however you want, so that's not an important thing. Okay, we'll come back to this in a few seconds. Okay, now let's start talking about the Whiteman axioms. Let's start talking about quantum fields. So quantum fields, according to Whiteman, are operator value distributions. On space-time. So let's forget about the operator part. Let's forget about space-time part. What does a distribution mean? Well, the classic example of a distribution is the Dirac delta. So the Dirac delta, as you know, is the non-function which satisfies the property that, so it's the thing that wants to be a function that satisfies this property. When I stick it in an integrand, and I hit it against some test function, then this is going to be, in this case, it's going to be centered at 0, so I'll get 0 out. So no function could possibly have this property, as you know, and so, but who cares? It doesn't stop you from saying delta is the thing for which this is true. So the way that we think about this mathematically is this is a linear functional on some vector space of functions, the vector space of test functions. It's a linear functional that sends, that associates, a linear functional sends a vector to a number, as you know. And so this one sends the vector f of x. It's a vector space of functions after all. It sends f of x to the number f of 0. So the Dirac delta is a great example of a distribution. We'll see more later. And in particular, the Dirac, this is the way to handle distributions. This is what we mean by distributions. So they're going to be maps from test functions to whatever. In this case, it's to numbers. In the case of an operator value distribution, it'll be to operators. And so so for us, for our quantum fields, x is really going to be x comma t, or z, if you prefer, where z is your parameter that runs around your space-time, your surface, the punctured disk in this baby example. And the operator is going to be a linear map that acts on some vector space. This vector space is going to be the space of states of your theory. So so our quantum fields, we're going to continue the practice of keeping z and z bar independent. We'll have more to say about this in a couple seconds. So our quantum fields, we'll write symbolically this thing as if it's a function of space-time, but of course it isn't. It's a function of space-time in the same sense that Dirac delta is a function of x. So it's a function of z, z bar, really a distribution of z, z bar, with the property that when I integrate around a test function, I integrate against a test function, our test functions are going to be just polynomials. So you want your test function to be, they're not going to be all possible functions. The Dirac delta isn't going to work if your function isn't continuous. Then you're not going to get a healthy thing. So you choose some dense subspace in your Hilbert space of that you're dealing with. So here it's going to be polynomials. You may as well take them to be monomials. And so this is going to be an integral around the origin, say, or whatever. We'll make it be the origin. And so this is exactly as Dirac delta was, this imaginary beast hit with this test function. It's going to be a linear functional in this sense. This is going to be some operator on some space, our Hilbert space, our space of states. So I'm going to use slightly fancy language for this. This just means all linear maps H, from H to H, and H is our space of states, whatever that means. So that's what a quantum field looks like. Well, this is so important to us that we're going to give it a name. So we're going to give it, this is not going to depend on Z anymore. The Z is being integrated out by our contour. And so we just get some operator that depends on M and N, and this is called the modes. It's like the Fourier modes of our quantum field. And so we can recover, at least formally, our quantum field if we want. We can recover it by by integrating over all M and N's of our modes. And then we have to choose. The wrong thing to do would be to write it like this. What we want is when we hit it with Zm and Zn bar, the residue is going to be, so I should probably throw in a 2 pi I or something here, but it's not important. So in order to get this to work out, we want to do something weird like this. And that way, if I formally apply this Fourier operation here, then what I'll pluck out is the Mn term. Okay? So this is the way I want to think about our quantum fields. This is the way I'm going to think about the vertex operators in our vertex operator algebra. Okay, and now we can make a definition. We can say a quantum field is holomorphic. So holomorphic usually applies just to functions, and we're talking about quantum fields, which are distributions. But we can still make a definition of holomorphic that I think we'd all agree with. It basically means that there's no Z bar contributions to this. So our quantum field is holomorphic if the modes are all equal to 0 for whenever n doesn't equal 0. Or maybe it should be -1 or something. Anyways, there's no Z bar dependence in this function. So that's what we mean when we say a quantum field is holomorphic. So what we're coming down to is our actual definition of a VOA. So what we have are, so in our string theory, we have two pieces to our string theory, two independent halves to our string theory. So we have our string, which is a loop, let's say, and we can have waves that go clockwise around the string at the speed of light, and we have waves that go counterclockwise around the string at the speed of light, and these just pass through each other. They're basically independent of each other. These are the two chiral halves of your string theory. So what we have is, so we have two chiral halves. Of our CFT. One is given by the holomorphic quantum fields, and the other one is given by the anti-holomorphic quantum fields. So your true CFT is a combination of these two. You splice these two halves together. We'll talk about this a little bit later. We'll start seeing examples of this thing going on. So the real CFT, the full CFT in all of its splendor consists of you have to splice together these things. But for many purposes, it suffices to consider the simpler beast, which is just the chiral halves. You consider them separately, do all the work you can, and then you understand how to splice these up. So it's a way to break up the understanding of the full CFT into the chiral pieces, which are much easier to understand separately, and then you have to worry about how to splice them up. So each one of these chiral halves is a VOA. So VOA is equal to the chiral half of your CFT. So really a CFT will have two VOAs. They don't have to be isomorphic in any sense. They'll have something to do with each other. And then you have to splice it together to get your full story. So we're ready to start describing what a VOA is. We can start our definition, our axiomatization, if you want to call it that, of a VOA. Well, we'll just be getting started, but so what a VOA is and so I should also say our two chiral halves mean our full Hilbert space here, a full space of states, is going to have sort of the right moving and the left moving states. So this is going to be a combination. So this is big, and so we take sort of the square root of it, which we'll call V, I guess, for VOA. And what this is going to be is the span of all of the holomorphic quantum fields applied to the vacuum. And we also get another space of states, chiral space of states, which would be the span of the anti-holomorphic, or the left-moving or right-moving, whatever, quantum fields applied to the vacuum. So quantum field is, so remember these are operator things. They're going to eat a state and spit out a state. Anyways, so you can think of this as the modes. So you can think of this maybe better as the span of the modes. So the modes here are going to be phi. We can delete one of the indices because we're dealing with just n equals -1 or whatever for the holomorphic ones. So the modes applied to this thing, that'll be a totally well-defined beast. We don't have to worry about whether it converges or not. And we take the span of all these, and the same down here. This will be phi of -1 or 0 or whatever it works out to be, n applied to our vacuum. And this will give us another vector space. It's convenient to not take the completion of this, so just take finite linear combinations, and you get two vector spaces. And this is what our VOA is. Our VOA is going to be a structure. The full CFT restricted to this thing is going to be the VOA. So VOA is a vector space. This will be a complex vector space because complex numbers are what you use in quantum mechanics. And it's going to be infinite dimensional, except in a silly example. So these are going to be infinite dimensional vector spaces. We'll call it V in honor of a VOA. So these are the states. These are what you could call the holomorphic states if you want. So it's a piece of the full. So the full space of states that I'll be calling H is going to consist of V tensor V bar plus a bunch of other stuff. Plus a bunch of other stuff. The other stuff is going to be built out of representations of this VOA, and the right moving and left moving VOAs. So you can get something like this, and then you should take the completion of all this to get your Hilbert space. Anyways, we'll talk more about that later. Okay, so VOA is going to consist of the square root of the holomorphic states, so half or a square root of your Hilbert space H, and buckets and buckets of quantum fields. We don't call them quantum fields. We honor string theory and call them vertex operators. But they're quantum fields. And these vertex operators, for now, we'll just give it the name phi z. And we know what they look like. These things look like the sum over all m of modes z minus m minus 1 to get the residue to work out right. Okay? Well, there's a hell of a lot more we can say about this, but that's what's going on so far. So that's the starting point of what a VOA is. Now, one thing about this that I should emphasize is this is a totally illegal sum. So this sum goes from minus infinity to plus infinity. And in general, all of these things, these coefficients here, these modes, are going to be non-zero. So this is totally This is totally illegal. Illegal is not a good word in math. It's not a helpful word, I should say, in math. So whenever you see the word illegal, you forget it, and you replace it with formal. So this is a formal sum. So you're always allowed to do formal things. And so let's play around with some formal sums, just to see what you get out of it. So let's do a formal sum. Here's the simplest possible sum of this illegal type. Sum over all of the integers of z to the n, right? So where does this converge? Does it converge at 0? Sorry? Yeah, so this has, for example, z to the minus 1, for example, in it, and actually terms even worse than that. How about 3? Does it converge at z equals 3? Who thinks it converges at z equals 3? Who's confident about that? Okay, that's a good sign. Okay, so this does not converge at z equals 3 or z equals 0. It doesn't converge anywhere. But converge is some, math isn't religion. So I don't know about physics. Maybe physics is. But math is not religion. And so who cares? We're doing with formal, illegal things anyway. So we can do whatever we want. Let's play around with this. See what we can do to play around with this. Let's multiply it. Let's multiply it by 3z to the 5th power minus 2z to the negative 1. Let's multiply this. See what we get. So we get sum from n equals minus infinity to infinity, surely. And we get 3z 5 plus n minus 2z n minus 1. I think we'd all agree. Well, surely no one's going to stop us from splitting this up. We put a 3 here, and we get z to the 5 plus n minus sum over all n's. I'm going to quit writing the integers down. There's a 2 here, I guess, and there's a z n minus 1. Does anyone have a suggestion for how we can simplify this a little bit more? Is this as good as we can do? Sure, yeah, let's just absorb it. 5 plus n, when we're summing over all the integers, is the same as summing over, have n prime equaling 5 plus n. So we can simplify this. And what we get is 3 sum from over all n's, n equals minus infinity to n equals plus infinity, of z to the n. Maybe I should call it n prime. And this is going to be minus 2 sum over all n double primes of z to the n double primes. It doesn't matter whether I call it primes or double primes. These are dummy variables. So I can just erase that. And, well, we know what this thing is. This is the thing we started with. So what we get is 3 minus 2 times the sum over all n of z to the n. What we get is, well, we get sum of z to the n. So we get something totally coherent. What would happen if I multiplied it by 8z to the 100 minus 40, okay, that's too big of a number, but 4 isn't. 4z to the minus 101 plus 2z to the 1 million times z to the n. Does anyone have a guess for what this is? Sorry? Nope. That's right. You might be worse at arithmetic than me, actually, so it's good to know. So I've learned something from this visit already. And so, right, so you're going to get this. And so more generally, at least if your function is reasonably nice, pz times z to the n is going to be equal to P1 z to the n, right? So we've seen something like this before. Or have we? I didn't get much sleep last night, so I could be. What's the lesson? This isn't going to hold for all functions, like cosine, who knows about cosine, but at least for polynomials, or Laurent polynomials, then we only have finitely many things to add up, so it's always going to converge. So if this is a Laurent polynomial, then this will work out. It's an easy theorem to say. What does this tell us? It tells us that there's a name for this thing. This thing should have a name. Evaluation map. This is a distribution, and the distribution has a name, something like this, right? What we have is a formal power series way to interpret a distribution. It really is a function in this sense. It's a formal function, but that's okay. It's not some weird abstract distribution, whatever that means, some functional on some vector space of functions. It's a formal series. Okay, and we can, if we take the derivative of our Dirac delta, again, we do everything formally. As long as we're a little bit careful, like we restrict ourselves to polynomials and we don't deal with cosines or something weird, then this is just going to be the sum over all n's of n times z to the n minus 1, I guess. And if we try to multiply this by something, let's just see what we get. Well, if we do exactly the same calculation we did before, we get, there's a 2 that comes in, we get some n, we get an n z to the, yeah, I shouldn't have made it this complicated, minus a sum of n z to the n minus 2, is it? Yeah, I shouldn't have made it this complicated. And so then we get boy, oh boy. Well, anyways, you can see what should happen. So we're going to change variables to get a derivative again. So it'll be shifting. This will be subtracting or adding or whatever some multiple of the Dirac delta. And same over here. And what we're going to end up with is a contribution coming from the derivative. So we're going to get something times the Dirac delta plus something times, the derivative of the Dirac delta. And this one should turn out to be the derivative of our function, evaluated at 1. And God knows what this one is. I'll let you work it out. This one, I might screw up if I push it much further. So you can take derivatives and it works out. It's sensible as well. So thinking about these things as distributions is completely taken algebraically by thinking of these as formal power series. So formal power series equals distributions. So it's a great accident, a happy accident, that actually this algebraic interpretation, the VOA interpretation of these things, is automatically takes care of the scariest bit of the quantum field, that it's an operator-valued distribution. The operator part comes from the modes. The distribution part comes from this being an illegal infinite sum of formal power series. And so formal power series just means you have to be a little bit careful. It's easy to get contradictions. So what you do is you restrict yourself to hitting it with test functions. So you hit it, our test functions here are going to be polynomials. So we're going to also need, shortly, Dirac deltas in more than one variable. So what should be the Dirac delta for two variables? What this is going to be is a formal power series with the miraculous property that some test function, which is going to be some Laurent polynomial in two variables, and we want this to equal the same distribution again times some number, so the specialization of this thing to z equals w. This isn't exactly the way that we had the Dirac delta before, because we had this integral which kind of cancels the Dirac delta. But this is the way that it is formulated in this formal power series way. Anyways, the way that works is to take your Dirac delta. I don't want to waste too much time on this. It's just going to be the sum of Zn or Wn over Zn. So you can talk about Dirac deltas in more than one variable. This is looking a little bit like the notation isn't quite right, because Dirac delta should mean that this is an additive notation, and really it's what's going on is a multiplicative thing. But that's probably because we're doing a Fourier version of this. It's not important. It's just you have to be a little bit careful about how these things are going to transform if you rescale variables and stuff like that. Anyways, so we have Dirac. We're going to be dealing later with Dirac deltas in more than one variable, and it's all handled in the same way, in a very natural way. Okay. Right, and so maybe I should also say something that, let's look at our formal power series. This is, again, this is our Dirac delta. This is the sum of the illegal sum over all integers. And let's square it, just for the hell of it. So let's multiply it by that and see what we get. Can anyone tell me what we get? Wow, it's easy to do. We get the sum over all m and n's of z m plus n. I think you'll agree that what you get is something that's bad. So this is an example of things you can't do. You have to be careful. So you multiply your distribution by a test function, and your distribution doesn't count as a test function. It has to be a polynomial. Okay? You can't square the Dirac delta. You can multiply the Dirac delta of x with the Dirac delta of y. That's different, but you can't multiply delta x with delta x. Okay? So you have to be careful about this. So they're formal power series. We have to be careful to make sure we're doing things legally, but you can. It's not hard to do. Okay, now let's continue with the definition of our VOA. So now in a normal quantum field theory, you have, for example, the standard model, you have a very small number of fields, of quantum fields. These are your building block quantum fields. So you have the left-handed electron and the left-handed neutrino, and you have your right electrons, and you have your quarks, various kinds, your photons, et cetera, et cetera. So you have all these different particles, but a finite number of them, and then these things generate all the other things. For reasons that'll be describing soon, in conformal field theory, it's natural to be far more generous with what you call a quantum field. So any local operator we're going to call a quantum field. So we're going to be much more accepting of quantum fields. So what I mean by this, well, the state field correspondence is a basic property of your conformal field theory. it ultimately comes down to the fact that our cylinder, our half-infinite cylinder, can get mapped to the punctured disk. And so the state field correspondence tells us that, so this does not hold in a general quantum field theory, but it does hold in your two-dimensional CFTs. Your state field correspondence tells you that there's a bijection between your fields, interpreted in this very generous sense, and your states. So the correspondence goes like this. If you take the limit as z goes to 0 of your quantum field, and you apply it to the vacuum, then this limit exists, and it equals some state. It equals a state that's going to correspond to your quantum field phi. And this map here, this correspondence here, is a bijection. So what this means for us, what this means for our VOA, is the different quantum fields. I just described it there with phi of z. We can reinterpret as phi. We don't need a second set of data. We can reinterpret as, we could reinterpret as phi of v. So we could use this notation, where v is the state that corresponds to this particular quantum field. And so the way that we write this is y of vz. So y should remind us of a vertex. And so this is the quantum field associated to the state v. So v is anything in our VOA, our state space big V, and we get some quantum field. Okay, so this is how we're going to parameterize all of the fields. They just correspond bijectively with the states, the vectors in our vector space. Okay, this is state field correspondence. So an example of this, the most important, the most boring state in our VOA is this vacuum that I've alluded to a couple times before. I'll define its properties a little bit later, but I can already say one of its properties right now. So this state field correspondence is one of the axioms of a VOA. And another axiom is that there's a special vector in your VOA, which we'll call the vacuum. It has lots of properties, and I'll write them down later. But one of the properties is that its quantum field is equal to the identity. So its modes are the identity and zeros. So it's just this thing here. Okay, and as I say, there's lots of other properties that the vacuum is going to have, but this is one of them. Okay. Now we should talk about the conformal symmetry. All these local symmetries. So what we know from physics is when you have some local symmetry, you have Noether's theorem arising, which gives you you have conserved currents. Conserved currents, in this case, is going to correspond to a quantum field, a vertex operator. That's called the stress energy tensor. Who cares what it means? So this is going to correspond by the state field correspondence to some state, and this is an important important quantum field. So this is an important state, and it's given a name because of that. It's called the conformal vector. So this, of course, lies inside our VOA by the state field correspondence, and it's a very important vector, and we'll have more to say about it later. So like any quantum field, any vertex operator, this one has modes. And so these modes, the way that we would write it if we were consistent is W subscript, omega subscript, n, z to the minus n minus 1. But unfortunately, we're not consistent. And so the way that this is usually written is ln z to the minus n minus 2. And Ln is, these are the conserved charges, Noether's conserved charges. Who cares what that means? And so what it's going to give you is, these things are going to give you a representation of our conformal algebra, or more precisely, it'll be a projective representation. Generally, in quantum field theory, quantum mechanics, you get projective representations of your groups because you have this array. You identify your state with any scalar multiple of it. You have this projective space thing. So the state vector v and the state vector 3 times v are the same. And so you get projective representations occurring all over the place, and that's what you get here, projective representation of our conformal Lie algebra. And so in terms of Lie algebras, what you get is the thing you should get plus a correction term. The correction term is going to be a term that commutes with everything. It's a central extension of our space. So we have some Dirac delta, so only sometimes does this term contribute. And then we have some prefactor. The 12 is conventional, but this other thing isn't. And so I'm sure you've all seen it before. This is called the Virasoro algebra. What it is a central extension. Whenever you have a projective representation, you get a true representation of a central extension of whatever beast, group, or Lie algebra you're dealing with. This is a central extension of our conformal Lie algebra, our infinite dimensional conformal Lie algebra. Okay. Well, these modes lie in endomorphisms of V. So in other words, they act on our space of states. And so what we get is Ln defines a representation on our VOA, V, a true representation of the Virasoro algebra. The central term is sent to a number, which we'll call little c. Little c is a complex number, and it's called the central charge. It's an important part of the story, but we're not going to focus too much on it. So anyways, we get a representation of our conformal symmetry. It translates to a representation of a central extension of the conformal symmetry, representation of the Virasoro algebra. Okay, and so one thing that the Virasoro does all kinds of things for us. Virasoro is going to be responsible for modularity, as we'll see a little bit later. Virasoro algebra tells you how your, this isn't a surprise, it tells you how your quantum fields, your vertex operators, maybe I shouldn't use phi notation anymore. So if I substitute in some function of z into this, then this relates back to some vertex operators at z with stuff in front. And the stuff comes from the Virasoro algebra. So the Virasoro algebra tells us how our quantum fields, our vertex operators, transform when we do mean things to our z variable, our coordinate. What else do I want to say about the Virasoro here? Oh yes, I have a lot more to say about the Virasoro. I'm not sure if I need to say that yet. So so the true conformal symmetries, the true, in other words, the group, the invertible conformal sims in R2 form a group SO 3, 1. So should be 3, 1. And this is over the reals. And so this is three-dimensional. Three-dimensional as a Lie algebra. I mean, this is true. I don't know what the dimension of this Lie group is. So what's the dimension of SO4? Anyways, it should be three-dimensional as a complex. So six-dimensional. SO4, is that six-dimensional? That's six-dimensional, I think. As a real thing, and so as a complex thing, it'll be three-dimensional. And so L plus or minus 1 and L naught span over the complex numbers this Lie algebra. And so this one corresponds to scalings. L1 corresponds to translations as a global symmetry, and L minus 1 is more complicated. But that's not so exciting. Oh yes, one thing that is exciting is, so remember what we said, Hamiltonian, which is the energy operator, is L naught plus L naught bar. So the Hamiltonian on our chiral theory is, we can throw away that, it's going to act trivially, is just L naught. But we can't use this anymore, we have to use this. So L naught is our Hamiltonian. Capital L naught is our Hamiltonian. So the eigenvalues are the energies. It's the energy operator after all. And so L naught will be diagonalizable on our Lie algebra, on our VOA, I should say. And so what that means is our VOA can be written as a sum over the spaces with fixed eigenvalue. So for most VOAs, at least for a while, until we get into the log VOAs, these are typically going to be sums from n equals 0 to infinity of Vn. And so typically, these Vn's are going to have finite dimension. And so Vn means the eigenspace of L naught, the energy operator, with eigenvalue n. And so n is the energy of all the states inside here. And so the vacuum is going to be fixed by these true symmetries. In particular, it's fixed by L naught. And so the vacuum lies inside V naught. And for whatever it's worth, the conformal vector, the second most important vector in your VOA, lies inside V2. These aren't axioms. These are derived from axioms of your VOA. These are just truths in any VOA. And what more do I? Oh yes, and then I have an important fact. And again, it's not an axiom. It's a consequence. Our modes respect this grading. So to make this more precise, if we take any vector that's inside graded k, so its energy is k, and we choose any, so then we look at its Lth mode, then it's going to take Vm to a well-defined space, M, and this is where I'm going to get it wrong. It's M plus k minus L minus 1, I think. So the modes respect the grading. Again, this is a theorem and it's not a theorem yet. It's a theorem when we get a little bit further. So if you want to think about this in terms of quivers, then this is what a VOA is at this point. What you have is a bunch of you have your vertices of your graph. So your vertices are going to correspond in the nicest cases. It's going to correspond to the numbers 0, energy 0, energy 1, energy 2, et cetera, et cetera. And let's take, let's imagine that V1 is three-dimensional. Let's make it slightly more interesting. Let's say V2 is three-dimensional. Then what that means is that you're going to have your quiver looks like this. And actually it goes, all of these will have 3 arrows in all directions between any two things, and that's just V2. If V22 is 33-dimensional, then you also have the V22 things that doesn't do exactly the same thing. They connect any two nodes with 22 arrows. It's just all hell breaks loose. This is not the right language at all to describe what a VOA is. And what this is a sign of is that we're missing some properties. It's way too chaotic right now. So just knowing that there's all these modes that are running between these different finite dimensional spaces is nowhere near enough. And so we're missing a key property of VOAs, the most important of all the axioms. And this most important of all axioms is called locality. And so that's what's going to put order into this. A VOA is still a complicated beast, but at least it's much more constrained than this. And so the final axiom, as I said, is locality. Now, to remind ourselves what locality basically means the only way I can adjust, the only way I can move that bottle mostly empty of water is to somehow outsource a disturbance. So either by concentrating a lot or throwing a piece of chalk or something like that. It's the only way I can adjust this bottle. So that's locality. So locality in an ordinary quantum field theory is it comes down. So what it means is if two things are space-like separated, then there can't be a signal between them. They can commute with each other. Anyways, locality in ordinary QFT, we have these really terribly improbable things called the equal time commutation relations. So in the simplest form, they look like this. So these commute, and you have relations that look like this. Who cares if they're not quite right? And so this is something that involves a direct delta, et cetera, et cetera. So you have relations that look like this. And so what form does this take in for a VOA? So this is the form, this is the answer, this is the key axiom of a VOA. So VOAs really start here. So you take two vertex operators, any two vertex operators, that means any two states, U and V. And you can never, these are distributions, so you can never multiply them if they have exactly the same space-time point. So you can't interact. This is totally illegal, of course, because you're doing weird things at the same space-time point, and we know you can't do that with distributions. So you change this to this, and what you end up with is, as you can sort of see from this, what this is going to be is a finite linear combination of Dirac deltas and their derivatives. So that's the form that locality takes. So I'm running out of time, so maybe I'll finish with spelling this out, and then we'll begin the next lecture with this, and then we'll very quickly, I'll do a simple example of a VOA and then dive into rational VOAs, et cetera, et cetera. So we have to find a better way to phrase this axiom. And so it turns out there's a theorem that says that if you have any finite linear combination of Dirac deltas and their derivatives have a weird property. These are completely captured by this. So I multiply this thing here with z minus w, and I get 0. This is the main axiom of VOAs, locality axiom. And this is equivalent to the statement that the commutator of any two quantum fields, any two vertex operators, is a finite linear combination of the Dirac delta and its derivatives. So, of course, we all have this urge to divide this by that. But dividing isn't allowed because what dividing means is you multiply by the inverse. That's what dividing means. And the inverse of this isn't a polynomial. It's some infinite series. Infinite series are fine, but we have to be careful. They're not test functions. And so we can't multiply some kind of a distribution with that. And so, so it's easy to see, and maybe we'll talk about it next class because we're out of time. Next lecture, we'll convince ourselves that this does not imply that these things commute. Anyways, this is the key axiom. So if you untangle this, then what you end up with is a triply infinite family of quadratic identities in the modes. And that's what completely constrains this. You now have all kinds of relations that this multitude of arrows have to satisfy. And that's what brings order into the chaos that we have right now. This is the key axiom of a VOA, and I've written it down, so we'll explore what this means a little bit next lecture and then move on from there. Okay.